Hello, Jai Hind, and I am Gaurav Srivastava, Assistant Professor in Electrical and Electronics Engineering Department in AKGEC Engineering College, Ghaziabad, and this college is affiliated to the Dr. APJ Abdul Kalam Technical University, Lucknow. So now today we have discussed about the unsymmetrical fault, another type of the shunt type of fault you can say, and there is a three classification in the unsymmetrical fault. That is the first one, LG fault, double L fault, and the double LG fault. Already we have discussed in a previous lecture how we can calculate it and why it is generated, and their numerical also we have discussed. Today we have discussed about unsymmetrical fault in the case of double line fault, that is known as the LL fault. So as per the name it suggests कि double line fault, that means two faults, you can say the two lines are collide parallelly, like line to line. These two lines are fault is generated in between these two lines. They two lines are the short circuited, and currently these here we have also included the fault impedances included as well. There is something like we have discussed without fault impedance and without neutral impedances also we have discussed this case in a later stage. Today we have discussed about double line fault, and right now like this is the neutral impedance connected in the fault ZF. But in the case of we have discussion, so that is all the fault conditions of the double line fault. And what is the fault condition? That is known as the boundary condition as well. So simply boundary conditions for the double L fault is known as the IA is equal to 0, because these faults occur in the phase B and the phase C. That is the short circuited, and that's why that is a phase A current having a 0 value. Okay. And second boundary condition, that is because of the IB current is flown in the phase B and the IC current is flown in the C phase, and these two phases are short circuited, then AB plus AB IB and the IC is equal to 0. That is the second boundary condition for the double L fault. And the third, because of the here there is a short circuited, so what will have the phase value, voltage value of the phase C, we can write down that is the VB minus IB ZF. And if we consider the case like ZF is equal to 0, what will happen? This third boundary conditions becomes VC is equal to VB. That means what is the phase value of the B voltage is equal to the phase value of the C voltages. So whenever we have discussed it without fault impedances, so that equations become this, and there the boundary conditions like IB is equal to IC, IA is equal to 0, and VB is equal to VC. So that is a boundary conditions become for the LL fault without ZF and ZN. Correct? So here something like this, with whenever we discussion about fault impedance including, then the equations becomes like this. Otherwise VB is equal to VC. Clear? So furthermore we have discussion like we have know the symmetrical equations conditions like IA naught, IA1, IA2 is equal to, what is the relation between symmetrical component and the phase value? That is like 1 by 3 1 1 1 1 alpha alpha square 1 alpha alpha square and IA IB IC. That is the relationship between the symmetrical components and the phase values. So already we have equation. So like now we have just taken one by one examples. Okay, like firstly condition we have taken. So that equation becomes like this. I can again explain you here. Just some rubbing. So here the first conditions taken, IA naught is equal to 1 by 3 IA plus IB plus IC. So here I is equal to 0, that is our first boundary condition, and IB plus IC is equal to 0, again we are using the second boundary conditions. Okay, so like now becomes I is not is equal to 0. That means in the double L fault, line to line fault, there is a positive sequence, zero sequence current are absent currently. So that is the zero sequence network is also absent, zero sequence impedances also is 0. So that's mean ki in the interconnection, when we find out the interconnection network for the double L fault, there is only other further that there is no 0. Then we can find out the positive or the negative sequence available or not. So depends on the conditions. Like then again we have taking the second equations, IA1 is equal to 1 by 3 IA plus alpha IB plus alpha square IC. So that means I again 0. So it becomes 1 by 3 alpha common layer alpha IB plus alpha square IC. That is becomes okay. Then we have to find out the third, IA2 is equal to again 1 by 3 alpha square IB plus alpha IC. So here we just find out the we are using ki calculation, for the calculation point of view we have just taken कि हाँ अगर हम यहाँ से relationship find out करें IB plus IC is equal to 0, that means IB is equal to minus IC, correct? Just put up this value here, we can find out IA1 is equal to minus of IA2. So that means कि here in the double L fault, positive and the negative sequence components available. Negative positive sequence is just positive sequence current is the negative of the negative with the negative sign, or the you can say the opposite side of the positive sequence network. So that means ki both positive and negative is available and the zero sequence current is absent. So whenever we have defined the circuit or you can develop the network, there is only positive and the negative is available with the opposite directions. And then furthermore, we have derived the whatever the value of the IA1, we just calculated here. So we have already using two boundary conditions, IA is equal to 0 and IB plus IC is equal to 0. So two boundary conditions are used right now. Now we are using third boundary conditions to calculate the symmetrical components fault current IA1. Clear? So like here we just taking the example ki haan, if we taking the VB plus is equal to VC. Okay. So when we have taken the VB is equal to VC with the fault impedance 0, like this, if the fault impedance is, right now we are just taking the fault impedance available, so net equation becomes IF IB into ZF. Clear? So just put up this value, how to phase value is derived, or you can say the distributed as like VB1 plus VB1, VB0, VB2 is equal to VC0 plus VC1 plus VC2 plus IB. Put the value of the IB. Okay. So again it is converted as a VA0 plus alpha VA1 plus alpha square VA1 plus alpha VB VA2 is equal to VA0 plus alpha VA1 plus alpha square VA2 plus IB ZF. So that's mean ki Va naught cancel, and here if we take in the value ki like alpha, so just changes. If we taking the alpha square is equal to Va1 minus Va2, correct, is equal to alpha Va1 minus Va2. This equation becomes like this. So now overall becomes expressions Va1 is equal to Va2 plus ZF Ia1. Just put up the value of the IB. So that is the IB की value, IB naught plus IB1 plus IB2. Clear? So just put up this value. So again that is the IA naught plus alpha IA1 plus alpha square IA2. So how we can calculate it and find out the final expression like this. Clear? So now from the above equation, just put up this value, because this equation here where we can find out this equation, because we know the symmetrical sequence network equation, that is the Va1 is equal to Ea minus Ia1 Z1, Va2 is equal to minus ka Ia2 Z2, and Va naught is equal to minus ka Ia naught Z naught. These equations known as the symmetrical network equation. Already we have defined and derived these equations from the symmetrical networks, and these equations can be used for the calculation of the fault current. So like now here just put up these values in terms of the last expression, where we can find out ki Va1 is equal to what the expression we have found, Va1 is equal to Va2 plus Z of Ia1. Clear? Va2 plus. Clear? So now put up Va1 is equal to Ea minus Ia1 Z1 is equal to minus Ia2 Z2 plus ZF Ia1. That's mean ki equations becomes ki like Ea is equal to so that is the equations becomes Ea is equal to Ia1 Z1 plus Z2 plus ZF, because this changes to the Ia2 is equal to minus ka Ia1. So this value becomes put up this, so that is the becomes positive, and this sign is becomes positive. So that is the overall configuration. That means Ia1 is equal to Ea by Z1 plus Z2 plus ZF. So that is the final expression. We have to find out the fault current. And this expression we can find out the positive and the negative sequence impedances are available, and the positive sequence networks are available, but the current flown in the positive negative is just opposite direction. So right now when we derive, or you can say that develop the equation, or you can say that develop the network, so that the positive is 0, so that's why there is a separate we can define here, and overall the positive and negative are the interconnections available like this. So that is the current IA1, and that is again IA2. That's why that are shown in the same direction, so that the value is just opposite. Similarly, that is the EA, and net voltage we can define as the VA1, and here this the voltage is defined as the VA2. Clear? So current is flowing, and right now as the impedance is also available here, so just connected the ZF here. So that is the interconnection network, and in this the positive and the negative circuit is connected, and the zero circuit is you can say the absent, or you can simply initial times of you just define the value like this for the single phase network. Yes, that is a Z naught, IA naught, VA naught. Clear? So that's become zero, इसलिए network से disconnected. So that is all about the double L fault, and now we have discussed about more in depth of the calculation part, ki how we calculated the fault current in the case of when the double L fault occurs at any point in the network shown in the figure. Okay, so right now that is a double L fault. We have taken one example, and the same question we are choosing here, and this questions again the capacity is same 10 MV and the 6.9 kV alternator, having the positive and the negative reactance is individual ki yahan 15% or the 0.15 per unit, and the X2 is 0.20 per unit, and the zero sequence reactance of that particular is given as the 5%, and now the neutral of the alternator is grounded through a reactance of 0.3. So that's mean ki you have the Zn is equal to 0.38 ohms. So we have to calculate Z neutral per unit value. Okay, original value is given. We have to find out the per unit values, and how we can calculate it? Zn by Z base. So how we calculated Z base is just using these values, and now there is a line to line fault occurs with the fault impedance in ZF, and now that is the ZF is also available, that is a 0.5 J per unit at the terminals of the alternator. Determine the line currents, fault currents, and the terminal voltages. So we have to, in as many questions and the many numericals, there is something asked to calculate the not only the line currents, they also calculated fault current, then also calculate the line current as well, and the terminal voltage find out. So right now we just taken one example ki like 15%, we have taken X1 is 0.5, X2 is 0.2, fault impedance 0.15, and X naught we have to calculate it completely. X naught is equal to how to, so firstly is convert as 0.38. So how we calculated 0.38 is equal to like this, 0.38 is equal to 0. And the double end fault, you just find out ki there is something confusion, because there is a in the numerical the value is given, and for your confusion point of view there is a neutral reactance is given and the fault impedances is given. So there is a something confusion ki like how to Z naught calculation. So Z naught is because basically 0. Why? Because already in the derivation we have find out there is a no zero sequence current flowing and the no zero impedances are available. So you can directly put up Z naught is equal to 0. So Z1 and Z2 is available and Z naught is equal to. That's why कि हाँ ये question mark that means कि आपका Z naught is equal to 0. Then we have calculated the IA1. How to calculate? The formula is IA1 is equal to EA by Z1 plus Z2. And also you can calculate the fault impedance ZF. Clear? So right now that is a 1 divided by 0.15 plus 0.2 plus fault impedance is 0.5. That is a 2. 3 plus 2.5, that is a minus ka 0.2 J per unit. IA2 is equal to negative of the IA1, that is a again you will calculate it, that is a 2 J per unit, and IA naught is equal to 0 because of zero sequence current is absent. So these values are calculated easily, and now we have to calculate ki like आपने you have to calculate IA1, IA2 and the IA naught. Then we have to calculate completely fault current. So that means IA is equal to IA naught plus IA1 plus IA naught 2 is equal to become 0. जो हमारे boundary conditions में था I is equal to 0 and the same value we have find out. And now find out the line current. Again for the phase B value. How to calculate the phase B? So base or you can say the fault current IF is equal to, you have just calculated कि हाँ fault current that is these because of the IB. So how much, because how you can this calculated 3 times of the, so yeah, here we just calculated 3 times of the IA1. So IA1 is calculated at the 36 J per unit, but we have to calculate I base. How do I calculate the I base? Here the MVA rating is given 10 into 1000, convert to the KVA, and here the voltage is given 6.9 into root 3. So that is the becomes value. You can say the 836.7 ampere. So right now, if you just changes the value, so fault current is become 3 times of IA1, that is a 6 into 838.7, it becomes the value. Clear? So that means fault current IB, you can directly calculate the IB here. How to calculate the IB? We just shown. IB is equal to IC. You have to calculate in the case of this when the fault impedance is 0. Then IB is equal to IC. Then IB you can find out the IB naught plus IB1 plus IB2, that becomes IA naught plus alpha square IA1 plus alpha IA2. So when it is 0, then alpha square IA1 की value, you have two values of the IA1 put up. IA1 is equal to, what the value we have find out, IA1 is equal to 2, okay, into minus 2 plus alpha minus 2 value. So that becomes 2 minus alpha square minus alpha, that becomes, clear, plus 2J per unit. So IB we have find out the value 2J per unit. So here the phase value is given, put up, and now we have to find out the terminal voltages. How we calculated the terminal voltages? The terminal voltages like this. Terminal voltages like we have the equations कि हाँ VA1 is equal to EA minus IA1 Z1. So here directly whenever you have put up 1 minus IA1, whatever the value here calculated, minus 2 J, and the Z1 is 0.15, ठीक है, with the J value. So these values becomes 0.7, for the calculation point of view, we have just write up V, and similarly we have the value of the VA2, that is 0 minus IA2 Z2. So that's why here equation you just say now VA2 is equal to minus IA2 Z2. So where the value, put up the value of the IA2, we have calculated the this, and VA naught is equal to 0 because of the minus IA naught and Z naught. The value of the IA naught is already we had derived, that is the values become 0. So voltage across the zero sequence network is the 0. So correspondingly we can calculate the phase components as well, that is the VA is equal to 1.1 and VB is equal to this per unit and VC is equal to this. And again we are just multiplying the value because of the these values are calculated in terms of the per unit. So we have to find out the exact value. So we have just using this value, जो आपका base voltage is given था 6.9 kV. So that's just using the in the terms of values. So numerical values, we just find out the phase value VA, VB, and the VC. So that's all about our. That is all about the LG fault and next double L fault. And next lecture we have completed the double LG fault so that we can conclude all the unsymmetrical types of fault. Thank you.